Hey, so today we are going to start a new chapter, right? So we have talked about efficient inference techniques with pruning, quantization, neural architecture search. We've also talked about those efficient training techniques, both on the cloud for large-scale distributed training without a lot of servers, and also on-device training on the edge using quantization, sparse update, tiny training engine, loop algorithm, etc. Right? So now we are going to switch gear to talk about a new chapter about those application-specific optimizations. So far, the techniques we have learned are all general purpose. No matter what kind of neural network it is, what kind of application it is, those are general techniques. However, there are still a lot of domain-specific techniques that is giving us a lot of opportunity to reduce the redundancy to further optimization. Right? So today we are going to talk about one of them, which is efficient point cloud optimization. So here's an overview about the opportunities for domain-specific optimizations for efficient AI computing, right? So apart from those general purpose optimization techniques like pruning and quantization, there's a lot of redundancy in different applications itself. So here I listed 4 examples we're going to cover in our lecture, both this week and also next week. Starting from point cloud, right? There's a lot of redundancy in the 3D dimension. So this is switching here from 2D vision to 3D vision. Not all the space is occupied by objects. A lot of places it's completely empty. There's no object over there. So the point cloud will be 0 in many places. So lots of spatial redundancy. Okay. And also, I choose these 4 applications because they are very widely used. For example, the point cloud recognition, both detection and segmentation, are widely used in autonomous driving tasks and also AR/VR tasks. So nowadays, if you look at an iPhone, there's a LiDAR. Okay? There's a LiDAR sensor right here. Right? So very crucial application for mobile vision and mobile AI. So we want to take advantage of the spatial redundancy and see how can we take advantage of those redundancies to reduce the computational workload and accelerate the inference. The second task are videos. Okay, so video is the biggest big data. There are a ton of hours of YouTube videos uploaded to YouTube every hour. Right? So how to understand them, be able to do a search, understand the videos, is very crucial. So video is adding a third dimension, which is the temporal dimension compared with the images. So higher dimensional, similar for the point cloud. One is adding another spatial dimension, the other is adding another temporal dimension on top of images. Right? So what's the consequence of that? Added a lot of computation, require a lot of memory. However, adjacent frames are very similar. Right? If you see adjacent frames, a person cannot move super fast. Right? So adjacent frames, lots of pixels are exactly the same. So that leads to the temporal redundancy. So we are going to think about techniques to model this, do this kind of temporal modeling in a more efficient manner to reduce this kind of temporal redundancy. And next, I'm going to talk about these generative models. Okay? For example, photo editing. Right? We can adjust certain pixels within an image, right? By using these generative models, by changing the nose, changing the hair color, changing the smile, changing the age. But we are not changing all the pixels. Right? So there's spatial redundancy in the 2D domain. And we are going to discuss techniques to compress these GAN models, even the recent diffusion models, especially when you are doing this kind of real-time photo editing on the tablets. Then you are not changing all the pixels. So in our latest work called SIG, we do sparse update and only compute the pixels that are edited. So that is a 2D spatial redundancy. Next task, widely used, is the natural language processing. So for natural language processing, we have many tokens in a sentence. However, in human language, not all the words are equal. In this case, as a visual trick, the film is almost perfect. So we don't need to see all the words. For example, we can just see film perfect. Then we can understand the sentiment. It's positive sentiment. Right? So only 2 tokens rather than 11 tokens. So here we can reduce the number of heads from 8 heads, from 12 heads to only 8 heads to take advantage of such total level redundancy. To preserve only 12% of the total computation while no lose of accuracy. So these are the examples of the big picture that we are going to learn this week and also next week. So spatial redundancy, spatially, and also temporal redundancy, 2D spatial redundancy, and also token level redundancy. So today, let's start with the first topic to talk about LiDARs, okay? 3D temporal spatial redundancy. How do we remove those redundancies? So this is the agenda for today. We are going to first introduce the 3D sensors and how is the point cloud generated by 3D sensors, followed by different ways of representing and processing 3D data, followed by efficient algorithms for deep learning on point cloud, and also efficient systems to implement and to support such efficient algorithms for point cloud. So 3D sensors are very widely available these days. For example, in VR headsets, in self-driving cars, this is the rotating part, this is the LiDAR sensor. And on our phones, so it's just the LiDAR sensor, it can get to know the distance of the objects, drones, etc. So this point cloud are collected by the LiDAR sensors. So the LiDAR sensor, so emit the wave, so we can calculate the range by this equation, the time times the light speed of light divided by 2, that give you the distance. Okay? So unlike cameras, so LiDAR sensor can get very accurate distance information. So this is an example of what does the data look like from the LiDAR sensors. So we can see different colors indicating the distance. So a point cloud is a collection of tuples of 3D points, including at P, which is their coordinates, x, y, z, as the coordinates, concatenated with a feature. So the feature would be C-dimensional, depending on your neural network architecture. So there's a different representation, very similar to the COO implementation, because the point cloud is highly sparse. Right? We cannot represent the entire space. Right? So we only pick those non-zero, those places that actually has a point over there, then we can represent that. So this is very similar to the COO representation in the sparse matrix representation. So before jumping to the efficiency implementation, let's first visit what are the applications. Why do we need to accelerate these point cloud applications? So point cloud is very widely used in modern mobile AI multimedia applications. This is an example of semantic segmentation in the Gates Computer Science Building at Stanford. This is before the renovation, actually. It was the shape when I was there, but now it's getting renovated. So we can label each voxel, okay, with the its corresponding category. For example, floor is blue, window is green, bookcase is red. So we can understand the indoor scene by using the point cloud. Okay? Very helpful for AR applications. This is another use case in autonomous driving. Okay? So on the top is the camera input. On the bottom is the LiDAR input, okay, which is the point cloud. And here we are doing detection, okay, drawing the 3D bounding box for the cars, for the pedestrians, okay? And also we are also doing tracking, okay, so that we can understand not only if there's person or vehicle, but also at the distance, where it is, how close it is with respect to our vehicle. And also, point cloud is widely used in scientific discovery. For example, in high energy physics, which is from one of our collaborators, they are doing particle discovery and using such high energy collider. And we want to filter out those particles, whether they are interesting particles or they are noise. Right? So representing particles is basically using the locations x, y, z, and also the energy and t, which is very similar to the representation of the point cloud, which is the x, y, z followed by the feature. Okay, so we find lots of the techniques we developed for point cloud can be seamlessly integrated into this high energy physics for particle discovery. Okay, so having introduced those applications, let's talk about what are the challenges of understanding the point cloud and point cloud recognition. So first of all, unlike images, okay, so image is pretty dense matrix. It can be 512 by 1K, for example. This is a lot of dense pixels that is very regular. Right? So it's dense and regular and can be processed by the CNNs that we have introduced so far. Unlike images, point cloud is extremely sparse. Since not every location is occupied by objects. Sometimes the sparsity, the density is less than 0.1%, very sparse. So they are not stored like a regular 2D matrix in the memory, but they have to be irregularly stored. So if they are contiguous in memory, they are not necessarily contiguous in the space, in the physical space. And existing kernels and libraries lacks the support for such sparse and irregular operations, which is not hardware friendly. Usually, they require specialized operators and systems to process such sparse and irregular data. Even existing sparse neural network accelerated frameworks is not targeting such a sparsity level. They're usually targeting 30%, 10%, 50% sparsity level, as we discussed from pruning. So this is fundamentally different from the sparsity of pruning. So let me pause for 1 second for you to think about what is the difference between the techniques to accelerate prune the neural network versus to accelerate the point cloud. We have learned pruning also brought sparsity. So what's the difference here?
So for this case, I think the input is more sparse versus for pruning, it's weights and
yeah, good point. The sparsity ratio is different. Here is more aggressive.
same, yeah.
Same thing. Yeah, more aggressive.
Here the data is sparse, but with pruning we made the weight metric sparse.
Right. One is weight matrix due to pruning, but this is dynamic. You don't know the sparsity pattern ahead of time. Right. So these are all adding challenges to efficiently process those point cloud efficiently. So that leads to computational problem. Right? So on the mobile side, it's going to quickly drain the battery if you are using the LiDAR for recognition on the phone. And for AR, VR applications, this gentleman is having a whole backpack of computers. Pretty heavy and limited the user experience. For self-driving cars, you don't want to have a whole trunk of computers, generate a lot of heat. There's no space to put your suitcase. So we want to make point cloud deep learning more efficient so that we can deploy them on resource-constrained devices. So this is the overview of our learning process, right? So we are going to learn how to represent this 3D data, this sparse data. And then we are going to talk about system and hardware support for such algorithms. Unlike images, the representation is very straightforward. Right? You have H by W by 3 RGB, 3 channels. It's a dense tensor to represent the image. But LiDAR is highly sparse. So there are people invented various methods to represent the 3D point cloud. We can use multi-view images from different perspectives to project the 3D object to 2D from different views, and use 2D neural nets to understand the 3D data. The first part. The second part, we'll talk about the voxel representation. Right? So we are going to quantize them, so by different chunks. And also, we can also use the sparse voxels. Since lots of different places, there's no voxel at all. There's also the direct point cloud representation, X, Y, Z, in the feature. And also there's alt-tree representation, where the granularity of the voxel is different. If there's more complicated structure, we use very fine-grained voxel. Okay? So voxel is in contrast of pixel. Okay? So pixel is in the 2D space, and voxel is in the 3D space. Alt-tree is just having different resolution of the voxel in different places. So we'll start with something very easy, using the pseudo image or multi-view image, okay, to project the 3D point cloud, okay, to this image-like representations. And we can use what we can do, which is 2D image recognition, to recognize something we cannot do. For example, the 3D shape understanding. In this example, these multi-view images can be obtained by rendering the point cloud from different viewing angles, from the side, from the top, from the left side, from the right-hand side. Okay? And we can apply these 2D scene on each perspective, on each 2D image, and aggregate the result by either average pooling or max pooling to obtain the final result. Okay? So use what we can do, what we have learned, which is 2D convolution, to understand 3D objects. So this is another method using a similar methodology, right, using the 2D convolution to understand 3D scenes. So what it does is basically having the entire 360 degree of the take a picture of 360 degree, okay, so that you can have the angle from 0 to 360 or 2 pi, and also you can have a certain angle to the top and to the bottom, so that you can have this spherical projection, also called range images. Range images, because we are having the entire 360 degree. Question here.
Sorry. Sure, that introduces some distortion into the.
Of course, yeah, that will introduce distortion. But since the training is also done by such images, as long as the training distortion is the same as the test, so the neural nets can learn such things. So the image from the range image is different from the normal image. So we can integrate that part during the training process. And after that, we can treat this spherical projected image, okay, as a normal H by W 2D image. So for example, if you want to do such semantic segmentation, we can just run a UNet, okay, from large resolution, and then with a couple of downsampling blocks, and then using upsample convolutions to do this dense prediction, very similar to 2D segmentation. So what is the pros and cons? Okay, so the pro is that all the techniques we have learned so far for 2D scenes can be directly used here to understand 3D scenes. Okay? And the con is exactly here, like I mentioned, they introduce geometric distortion. Okay? For more information, you can refer to this RangeNet to see more detailed implementation. Apart from range view projection, so we can also do the bird eye view projection. So what is a bird eye view? As if you are a bird looking down from the top, right? So this is the example of the bird view. We are looking down from the top. Okay? Very popular technique using the bird eye view is called the point pillars. Okay, it's doing the Cartesian projection. Okay, so assuming that in only one XY location, there cannot be multiple objects stacked together. So we are projecting the 3D space into 2D space, and assuming that you cannot have a vehicle on top of another vehicle. Right? That's why we are actually doing this pooling. It's also called pillar pooling. The entire pillar that share the same XY location but different Z location, we're projecting them to the same XY location and Z location. So this is like a pillar. So everything within this pillar will be projected to the 2D space, assuming there is not a vehicle on top of another vehicle or a pedestrian on top of another vehicle. And here we have a couple of hyperparameters. For example, P is the number of pillars, roughly 10K pillars. And N is the maximum number of points within a pillar. It's roughly 20. If it is above 20, we are going to cap it. And the D and C is the input and output channel. So we are going to do some feature selection on the learned features, and then we are going to continue with the 2D convolution. Since after pillar pooling, we are operating exactly on the 2D image rather than 3D, since we already projected the 3D information into 2D. So after that, we can just use the normal 2D scene whenever you have to do the detection or segmentation. Okay? So after this part, it's entirely the same with 2D scene. So one problem that might arise from this bird eye view projection is that the density, right, for point cloud is denser in the nearby region, but very sparse in the faraway region. Right? So if you're just using the Cartesian bird eye view, right, for the places that is very close to the LiDAR, the points are denser, but the places where it's very far away from the vehicle, okay, it's going to be very sparse. So people invented another way to represent that polar ADV. Right? So we can convert it from this Cartesian coordinates into this polar coordinates, right, which is represented not by x and y, but it's represented by rho and theta. Right? Rho is the distance from the center, and theta is the angle. So in this method, we can allocate a larger space for these faraway areas. Okay? Hopefully, there are more points in that region. Okay? And smaller physical space when rho is closer to us. So we can run convolution neural nets on such, for example, 3x3 convolution on such a grid in a similar manner of using a Cartesian space. So what's the difference here? The neighbors. if you rotate by 360 degrees, actually degree 0 and 2 pi, they are actually neighbors. Okay, so make sure when doing convolution, we are going to do proper padding so that we can acknowledge the 0 and actually 2 pi, they are actually neighbors. So when running convolution, they should be convolved together. So this is the polar projection. So this is illustrating the process where we are doing the ring connected convolution. Right? So for example, R and 0, R and 1.99, something very closer to 2 pi, are very close to each other. We should be convolved together. This convolution is related to finding neighbors. This is a special thing we have to take care of in rings. Okay, so we conclude the first part, which is representing these point cloud, 3D point clouds by 2D images, either in different perspectives or in the bird eye view. In bird eye view, we talk about Cartesian and also the polar methods. Okay? So now let's switch here to talk about those dense voxels. Okay? So let's write 3D point cloud into dense voxel representation. So this is an example of this object. So we can use different resolution of the voxel size. It's a method of actually of quantization. Right? If you use finer granularity, you have a smaller voxel. Okay? So the information loss is much smaller. As we increase the voxel size, it gets coarser and coarser granularity. Okay? If we have a pretty big voxel size, we actually lose a lot of information, for example, the lag. So the trade-off here is if we're using a much smaller voxel size, we have many voxels, which is going to take a lot of memory to store those voxels. But if you use a larger voxel size, we're going to lose a lot of information. So that is a trade-off. And here we are basically doing, there's familiar with this is doing the quantization. Everything rounded. We have a 4D tensor, which is upper bound of all the pixels, and then we insert a feature into a location into the 4D tensor V. So this is basically deep learning on these voxels. So we have occupancy rate, and VoxNet is already attempt to do deep learning on these voxel arrays. Okay? So it's very straightforward. We simply need to generalize from 2D scenes to 3D, right? Adding another dimension in the kernels. So there are other methods, okay, to run 3D scene on voxelized point cloud. For example, this method is suffering from overfitting issue, so we want to supervise in a stronger manner. So here, this is actually predicting the classification labels from partial voxel feature maps. Here we have 4 parts, actually 8 parts. 8 parts. And we try to make a prediction for each part. And finally, we can average them together to add another supervision. We can also do this orientation pooling on the right-hand side. For example, we can make a prediction. So this is a chair, right? We can rotate the chair in different angles. And we're going to pass each as a separate input into the same 3D scene, and we are going to give independent predictions. Finally, we are going to average them together by pooling, okay, to give the final classification result. So, which is a method to try to add stronger regularization and prevent overfitting. So, what's the drawback for such voxel-based method? So, we can imagine as we have a larger and larger resolution, just like the animation we have seen just now, the the GQ memory is going to grow cubically with the voxel resolution. So if the resolution is like 50 or 100, that require roughly with 8 gigabyte memory, you will lose a lot of information. Right? So the GQ memory is going very fast. But if we have a smaller resolution, for example, we have only like 50 or 100, the information loss, the distinguishable points is going to decrease very sharply. If you have a very coarse granularity, just like this example, lots of points are merged together and cannot be distinguished if we increase the voxel, increase the granularity. It becomes very coarse grained. So that saves the memory, but the number of distinguishable points is also very low. So with 8 gigabytes of GPU memory, more than 40% of information is lost. So we need better representations. Okay? That comes the point set, which is to process the 3D point cloud as an ordered set of points. So this is very famous work on PointNet. Just directly processing the point cloud using the MLP, the multi-layer perception. Okay? So the input is endpoints and feature detection, and then we just transform them using matrix modification. Okay? Passing it directly, pass it through many multi-layer perceptions. Okay? So here we have a TNet, which is a smaller point net that learned the linear transformation matrix. And the intuition is to rotate the input point cloud to a canonical view. And there's no constraint that this has to be a linear transformation matrix, rotation matrix. It can be any linear transformation matrix that is learned end to end. So here it's just many MLPs, many multi-layer perceptions, dealing on the n number of points. And finally, we are going to concatenate the global feature here with the local feature to do the output segmentation, output prediction. So what is the drawback limitation for such point net-based method? So all the endpoints, we are just passing them through a multi-layer perception. There is no interaction between the points. So each point, if it has n dimensions, and then we pass it through a n by m matrix, so it's going to be m dimensions. So there is no interaction between the points. Okay? But convolution and scene understanding is all about understanding the neighborhood. So that comes to follow-up work called PointNet++, okay, which is adding the neighborhood modeling into the process. Okay? For example, I'm trying to model this one. I want to also, similar to 2D convolution, I want to know what is its neighbors. And I want to run convolution or some MLP just on its neighbors. Okay? So people have invented several techniques to find a neighbor. For example, using the k nearest neighbor to find the k points that is closest to it. Or we can use the fall query using a fixed distance. So everything that falls within this distance belongs to my neighbor. Okay? So one of them gives a fixed number of neighbors. The other is giving a fixed distance. Okay? So they share some similarities, but kind of different. Okay? So now we have the notation of neighborhood. Okay? So that's a good point where we can do this neighborhood modeling from different layers. Okay? Segmentation and classification. So this is basically applying PointNet in a hierarchical manner. So we have the neighborhood modeling capability. So we can also try to understand the point cloud as a graph. Right? Graph, the edges, and also have the nodes. So each node is a point. So we can use the feature space when we are trying to model the neighborhood. Previously, we are just using the physical space by checking the distance, either using KNN, k nearest neighbor, or using the furthest point sum, either using the KNN or use the bulk query. So the distance is in the physical space. But here we can measure, define the neighborhood in the feature space. And feature space is not only containing the XYZ information, but also the feature information. Then we can build the neighbor graph dynamically. Okay, so what's the limitation so far? For both .NET++ and also DGCN, no matter which the relative location you are compared with the centroid, we are actually applying the same weights for different neighbors. This is not the case for 2D CN. Right? So in a 2D CN, the weight for these pixels are completely different. Okay, this is W minus 1 minus 1. This is W00. This is W plus 1 plus 1 plus 1. Okay? For different neighbors, we are using different weights to multiply them. Okay, for 2D CN. But that is quite difficult for 3D CN since it's not regular. It's hard to determine what is distance. Right? What is W minus 1 minus 1? What is W minus 1 plus 1? So is it possible, okay, to use different weights for different neighbors? Okay? For this neighbor and this neighbor, apparently one is on the top, one is on the bottom. It should be convolved with different weights. So that they use this point CN, okay, which is learning to permute neighborhood points and apply a fixed kernel. So here we have this NLP as basically learning this K by K transformation matrix, which is applying a different kernel on different locations. Different from .NET, .NET++, etc. They're all based on symmetric functions. No matter where you are, compared with the centroid, we are going to apply the same transformation. But in CN, the author attempt to permute the K nearest neighborhood points into a canonical order with the learned permutation matrix, and then apply this regular 1D convolution to aggregate the 2D, to aggregate the neighborhood features. So initially, the relative location for different points may not be the same, but after applying this transformation matrix, it's saying trying to permute them or project them into a canonical order so that we can apply the same set of kernels in different locations. And point conv is another branch of work that is applying dynamic weights for neighborhood points. Okay, so we have several features. Okay, we have K points. So we are multiplying both the density. Okay? Imagine if a point is denser for its neighbors versus much sparse with its neighbors, the weights should be different. So multiplying the original feature with the density and also the distance of this point compared with the local point. Okay? So that is very similar to 2D convolution. We have the notion of the relative location compared between particular kernel point versus the central point. So here we have subtract the P0 from the other points, which is measuring the distance. Okay? So we apply both the density and also the relative distance with respect to the centroid to do the convolution. That way, we are not using the same convolution kernel for all the points anymore. But here we are considering the distance between the point to the central point, and also we are considering the density of such points. And there's another way of method that is using the interpolation to try to differentiate the relative location. So we can find from the centroid, we find 6 equal distance locations. We are trying to learn the weight on those blue points. What about for other points that does not lie on one of the 6 points? We're going to do the interpolation based on the relative distance. Okay? So that we can have different kernel for different locations. So all these methods we can feel is very complicated, right? So before doing the convolution, we have to calculate the kernel first. Unlike 2D convolution, where the kernel we have a very regular pattern, but here we have to do either interpolation or combine that with the density. There's a lot of overhead to do the kernel computation. This is overhead from this kernel computation compared with the payload or the actual workload when we are doing the red part, which is the convolution. For DGCN, PointCN, SpiderCN, a lot of the computation is actually occupied by such irregular axes and also calculating the computation on the fly, right? So conventional 2D scenes, the kernel numbers are fixed, but here the kernel itself has to be computed on the fly, which is inefficient. One scene only a very small portion, maybe 1/8 of the computation is actually happening on arithmetic operations. And all the remaining 7/8, they're all wasted on irregular memory access and also the kernel computation. There's another line of work trying to improve the efficiency of point cloud via such fast downsampling, okay? Trying to but the downsampling time itself can actually scale very quickly as the number of points grows. Let's continue our discussion about sparse voxel representation. Okay, so previously we talked about those dense voxels. Basically, we are quantizing the space and using this h by w by depth by channel, this 4-dimensional tensor to represent them. However, there's a huge waste, right? So can we just quantize those coordinates that is non-sparse? Okay? When we have the actual object in that location, then we have a point. Otherwise, we don't save that point. Okay? So now the memory cost is only proportional to the actual point. If somewhere like here there's no object, then we don't need to store that point. Okay. So why do we use sparse voxels instead of point cloud? Because now we have integer coordinates. We are quantizing the space so that we can have integer coordinates, okay? Which is making the neighborhood query much easier. For example, x plus 1 is indicating its very first neighbor to the right. So running convolution on sparse point cloud is different from this conventional convolution, right? So for conventional convolution, the sparsity will get denser and denser, and we call it dilation. Okay, we start with something, maybe a ring that is very sparse to begin with. So after a few layers of a convolution, it will gradually become denser, right? So this is the convolution. As long as this particular location, one of them is non-zero, then the output will become non-zero. Okay? So if you observe the sparsity of the input versus the sparsity of the output, this is always denser compared with the input, right? So after a couple of layers, what is the problem here? If we use this conventional convolution on the point cloud representation, sparse point cloud representation, after a while, the whole space will be non-zero, right? That require a lot of storage and memory to store those activations, right? So instead, people are using this thing called sparse convolution to represent to do modeling on the 3D point cloud. Okay, so what is a sparse convolution? The sparsity pattern of the input and output are exactly the same, right? So no matter how many layers you have, we always have the same sparsity pattern and sparsity ratio. And we only apply convolution to those outputs where there is a corresponding input, right? So the kernel itself is not a sparse kernel, but the output is sparse. Okay, so the output sparse pattern is the same as the input sparsity pattern. Okay, so we only apply convolution to the output location where there's actually an input. So the sparsity pattern of the output will stay the same no matter how many layers you pass it through. Sparse convolution is actually not quite efficient on GPUs. So compared with the actual matrix multiplication, the GMM, actually a very large proportion is actually consumed by this data movement, okay, due to the sparsity and structuring, orchestrating the data, both for segmenting segmentation and also for object detection tasks. For object detection, this problem is even more severe, where this computation is occupying only one quarter of the total computation. Therefore, there's another way, actually trying to make it more efficient, which is using the octree method. So octree is basically dividing a cube by 8 sub components, right? And each component can further have its child, right? We can use different granularity to represent different locations. For example, for this location, there might be some fine-grained details that we might have to pay attention to. Then we have a more fine-grained representation at this location, versus at this location we have a pretty fine, coarse-grained representation where it doesn't have any child. Okay? So this is another irregular data structure that can recursively divide the 3D space into a finer granularity voxel grids. Let's look at this representation for this bed. Using the dense 3D ConvNet, we either have coarse granularity or fine granularity. Okay, but using the octree, we can use different granularities. For these locations, which is completely a white space, there's no object here, we can use pretty coarse-grained representation. Well, for these finer granularity, these kind of details, okay, we can use finer granularity of the representation, right? So if you cannot see remotely clearly from the remote, here we have a mid-sized voxel. Here we have a pretty big voxel, but here we have a pretty small voxel. Okay, so different granularities for different for more details versus less details, trading off between details versus the memory. So that naturally comes the question, can we use some kind of hybrid representation that can give us the best of both worlds, right? So remember, the memory access is very expensive, right? So our goal is to use a hybrid method that try to reduce the DRAM access and also try to avoid those random memory access to have consecutive memory access. And also the bottleneck for those point and voxel-based methods are different. Okay, so for these voxel-based methods, the memory grows cubically with the voxel's resolution. So memory is the constraint, versus irregularity is the constraint for these point-based methods. Point-based method is more memory efficient because we only represent those non-zero points, versus the voxel, it may contain the information for both both the non-zero point and also the uninteresting point. So we want to have two branches to get the best of both worlds, right? We want to have a voxel branch and also a point branch. Okay, so the point-based branch
is just doing the point-based feature transformation, which is very fine-grained. It happens on individual points to the transformation with no neighborhood modeling, right? While on the voxel branch, we can have this neighborhood modeling since we can do 3D convolution on the voxel branch. But if we apply voxel branch itself, it needs to have high resolution to capture those details. But in this example, the details can be offloaded to the MLP to the point branch to calculate those detailed information. While those coarse-grained big picture can be captured by the voxel-based branch. Okay, so the voxel branch has a better regularity since it is dense and no irregular access. We don't have to generate these dynamic kernels, right? It's a better choice for neighborhood information aggregation since it is regular. But the point-based branch can keep very high resolution, right? Since it is only representing those non-zero elements and can alleviate the information loss from this coarse-grained voxel branch. So let's visualize the voxel branch versus the point branch. The point branch is exactly capturing those edges and details, okay, versus the voxel branch, which is more coarse granularity, is capturing those big pictures, like the large areas and big pictures, versus point-based branch is capturing those details. So this PVCN, standing for point voxel CN, is fast and accurate, right? So this is comparing the accuracy and latency trade-off versus the accuracy and the memory trade-off, right? So this is comparing with spider CN versus the point CN, and this is PVCN, ranges from 2.7 to 7.9 times speed up. Other networks like 3D UNet, Spider CN, PointNet++ are also in the figure. On the right-hand side, we are comparing the GPU memory. Okay, so this is PVCN. So compared with this 3D, compared with PointNet++ or this point CVN, the memory saving ranges from 1.5 to 2.4x. So this is the demo for 3D scenes, the indoor scene segmentation, comparing PointNet versus PVCN, right? So it requires a smaller amount of memory, 1.2 gigabytes versus 1.9 gigabytes, almost 2x faster. Okay? So PointNet versus PVCN, almost 2x faster. So the limitation of point voxel CN is that when we are going to have a larger input scene, like the outdoor space rather than indoor space, the objects, like a person, in the voxel branch becomes only a few voxels, right? So this is too coarse, and we can lose a lot of information if the scene is too large. So what's the solution for that? So rather than having this coarse-grained and dense voxel branch, we can have a more fine-grained sparse voxel branch, right? So that debuts this sparse point voxel convolution, short for SPVconv, right? So we are using a sparse voxel branch instead of a dense voxel branch. And here are the features extracted from the point-based branch. Okay, we can see those are the small stuff like the person, the cyclist, or the trunk, right? And also we can perform neural architecture search to balance the computation and also balance the capacity of these two branches, right? We have the sparse point-based, we have the point-based branch. We also have the sparse voxel-based branch. How do we tune those dimensions? Okay, so we are using a similar technique we learned from the once-for-all network. We first train the supernet, okay, and then we get a sub-network similar with OFA, which you did for lab 3, and then we use evolutionary search to find the best trade-off between the accuracy and latency by mutation and crossover. And finally, after that, we can have a much better Pareto curve. So this is computation versus accuracy, and this is the GPU latency versus the accuracy, right? And the search cost is actually much lower than efficient net. Okay, so this is combining the efficient architecture, efficient design space versus efficiently searching on the search space. Another follow-up work, so by using the hybrid method, is this range point voxel convolution, right? RPV conv. So apart from the voxel branch and the point branch that we introduced just now, this work has another range image which we introduced in the beginning of the lecture, right? We have the from 0 to 360 degree. It has some distortion, but it can project 3D scene into 2D image. Okay? And we are combining these three branches, okay? Either using conv2-3D for voxel branch, conv2D for the range image, and also using the MLP for the point branch. They exchange information by this voxel to point to voxel, and also range to point, and also point to range. Okay? And finally, they can predict the pixel-wise prediction. Right? So this is another approach, which is getting popular these days. Okay, so from a single sensor to multiple sensor, usually in order to do this real-world applications, like auto-driving applications, multi-sensor fusion is very crucial, right? We have not only a lot of cameras, but also a lot of LiDARs and even radars, right? So we have to define the task a bit more one step further by considering multiple tasks and multiple sensors. Okay? Multiple tasks including detecting the vehicles, segmenting the lanes and drivable regions, and also be able to fuse the cameras, okay, which produces dense images, and LiDARs, which is produce sparse point cloud. Okay? And we need two branches of data flow, one dense branch for the camera and another sparse branch for the LiDAR. Right? So that adds a lot of difficulty and challenges for efficient computing on top of such a hybrid understanding of point cloud and also the images. Right? So actually, we propose this method called BEV fusion that fuse the multiple sensors to perform multiple tasks in the bird eye view. Right? So we have a dense image branch and also a sparse point branch. We do feature extraction on both of them, and then we project them to the bird eye view, right? Assuming there's not a vehicle on top of another vehicle, and then we fuse them in the bird eye view. Conventional method either fuse the point to the image or fuse the image to the point. Okay, both of them lose information, and here we actually are choosing a third party, which is the BEV space as the target place to fuse the two different branches. Okay, and for different tasks, we just use different heads to perform different tasks. So this is a demo for BEV fusion from multi-view camera and also a LiDAR. We want to perform this 3D object detection and also the BEV map segmentation for the drivable region, for pedestrians, for walkways, etc. Okay, and here we can accurately detect the cars, the vehicles, from 3 cameras in the front, 3 cameras in the back, and we can fuse them together. The LiDAR-based only baseline does not perform well in the rainy weather, right? So the fused method can use camera to compensate for that. And similarly, in the night view, okay, the camera only baseline does not perform well. Lots of the objects are actually lost. Okay, but adding camera, BEV fusion, can do a better job in those low light conditions. And this is showing the baseline method of running about 5 FPS on RTX 3090 GPU versus we can run about 8.4 frames per second on the same GPU. Currently, this method is ranking first on the Waymo leaderboard, which is a very popular leaderboard produced by Waymo this is to do object detection, 3D object detection. Okay, so we just want to revisit different methods of 3D representations. By using multi-view images, we lose information and have distortion, right? And by using the voxels, the memory grows cubically with the resolution and is not scalable. And then we introduce the point cloud representation, which results in irregular access and dynamic kernel overhead. Then we introduced the sparse voxels. Okay, it has high accuracy, good scalability, and very widely used, but it requires efficient system support. Okay, so this method, sparse voxels, is probably the most widely used method these days, especially combined with voxel representation using a hybrid approach is very popular. And aux tree is another way, but not quite popular these days. It's challenging to define convolution on aux trees. Okay, so now let's switch gears to talk about how to use design efficient systems to support different algorithms, right? So first of all, the convolution on sparse point cloud is fundamentally different from the normal 2D convolution on images, where on 2D images, the convolution is very regular, and we have output for each output for each input. It is going to interact with each location on the kernel. Therefore, if the kernel is 3 by 3, the one input is going to interact with 9 outputs in the dense 2D convolution. But in sparse convolution, not all the outputs will interact with the input, with a certain input, right? So here, only this input is actually only contributing to 2 outputs. Okay, so only 2 outputs out of 9, right? So the number of multiplications is sparse and much less than the dense case. So therefore, we need to know what is the mapping for a particular kernel location. Like this is for kernel W-1, -1. Among these, we have 5 points in total, okay, 5 by Cin. Actually, only 2 of them is going to interact with W-1 and -1, right? Which is here, P0, okay, which is going to contribute to Q1 by interacting with W-1, -1, okay? And this is another pair, P3 and Q4, okay? So this is actually, we probably need to adjust the slide here. P3 and Q4 interacting with W-1 and W-1 inconsistent with here. Therefore, it's only a subset of all the points. Okay, we are not trying to use all the input points, but only 2 out of 5 points are going to interact with W-1 and -1, right? Recall in 2D convolution, all the inputs are going to interact with a certain kernel, right? But this is not the case for sparse convolution. And for another kernel, which is W-1, W-1, 0, okay, only 1 input is going to interact with that and contributing to 1 output, which is W-1 and 0. Okay? And these are the points that is going to interact with W00. This is the only one that is guaranteed to have all the inputs interact with that to produce all the outputs, since that's the definition for sparse convolution, where the sparsity pattern for input and output are exactly the same. For W10, okay, we have only P3. Okay, it's going to interact with W10 and produce this one, which is which is Q1, right? Which is Q1. Okay, and finally we have this P1 interacting with W11, and also P4 interacting with W11 to produce Q0 and Q3. Right? So all this complication is showing that we need a proper mapping for the input, the kernel, and the output, and that is not regular. So to make it easier, we built this tool called Torch Sparse, okay, that performs this 3D sparse convolution so that we can use the same interface as the 2D convolution. So we first construct this output coordinate construction, right? So similar to what we just described, not all the input-output pairs are interacting with the same kernel. And then we do the map search, followed by diffuse, the locality aware, scatter and gather, and finally with adaptive grouped matmul. Okay, so the interface of using the sparse convolution is exactly the same as the original Conv2D. Okay, everything is the same. You just change the function name. So this is the overview of the optimization for torch sparse, which is mostly concentrated among dealing with sparsity, right? So with sparsity, the workload is actually quite different. Some of the kernels interact with only a few points. Some of the kernels interact with a lot of kernels, right? So that makes the computation very irregular and fragmented. So what we are doing here is to do adaptive grouping. We group many similar the kernels with similar workload together. And sometimes we even pad redundant computation, pad zeros to those that has very little workload to pad them to make sure these 4 multiplications have exactly the same workload, so that we can apply this batched matrix multiplication called BMM on these different kernels. Okay, so this is one extreme of having separate computation for different matrix multiplications. So the computation overhead is the best. You have no overhead, but the computation irregularity is the worst. Another extreme, we are batching everything to the largest of these among these kernels. Okay, but this has a lot of computation overhead, although it has perfect regularity. So actually, what we are doing is computation with grouping to adaptively group them together, right? So the computations, the overhead is smaller, and the regularity is also worse, but it's still pretty good compared with the left scenario. So as we can imagine, as we increase the number of groups, the latency, the speed up first gets better and then get worse. Okay, because initially it gets better because the irregularity problem is better, but later it will get worse because those padding overhead will kill the efficiency and generate a lot of redundant computation. So this is comparing the result of matrix multiplication optimizations with fixed grouping versus adaptive grouping. So with grouping, by fusing padding a lot of kernels together, you can do a lot more better than this baseline, right? Having a higher flops per second. Although the fixed grouping, okay, will have a higher flops per second, but the actual speed up is worse compared with adaptive grouping because TOPS per second doesn't care if the computation is useful or redundant, right? So here we are doing a lot of redundant padding, make the TOPS per second pretty high, but it's actually computing a lot of redundant workload. The final speed up is actually not as good as adaptive grouping. Okay, so the take home here is that we want to trade the regularity trade the computation for regularity, right? Sometimes we are actually doing some redundant computation, but actually the speed is actually better than if we do no redundant computation, but it's purely irregular. There's some other philosophy, which is caching, right? The sequence matters. If you access 0.0, 0.3, and 0.95077, it has very poor regularity, right? So a lot of cache miss. But rather, we want to start with 1 point, makes it fixed, okay? And then run all the kernels that is going to interact with this point before we are going to throw that away and move to the next point. So altogether, torch sparse is roughly from 1.7 to 2x faster for this segmentation and detaching tasks. So mostly, we are actually reducing the overhead of data movement. And finally, hardware support, right? So accelerating point cloud is pretty challenging. There's plenty of accelerators for this 2D vision, 2D scenes with dense inputs or sparse pruned weights, but very limited research investigated 3D vision with sparse input, okay, which is fundamentally different. The sparsity is fundamentally different from pruning and from the redo function. So point cloud is very it is spatially sparse and quite different from the existing sparsities. And the sparsity pattern is also forced to be the same as the input as another constraint. So here the key idea is that we want to bring many different methods, like furthest point sampling when we are trying to do the neighborhood modeling, which is widely used, point net plus plus point cn. Okay, since we have to calculate the distance and find the biggest distance. Okay, the distance is defined as the mean among all the points. The smallest distance with the point cloud is defined as the mean, and I'm trying to find the max of that. Right. So here we are utilizing a sorting array to deal with that. And the same sorting array can achieve the top k, okay, for example, using the k nearest neighbor or using those bulk query methods. And the same sorting array can also deal with the kernel mapping, which is in the sparse component. For example, here to find the kernel mapping for w minus 1 minus 1, we first lay out the matrix together. Okay, so exactly the same coordinates for input point cloud and output point cloud, and then we are going to shift it. Okay, shift it toward +1 +1, which is exactly negating this minus 1 minus 1, right? And after the shift, we're going to calculate the intersection, okay, the common non-zeros. Okay, so here we have several common non-zeros, Q1 and P0, and Q4 and P3, right? So therefore, we have this Q1 and P0 and Q4 and P3 as the non-zero input-output pair corresponding to W minus 1 minus 1. Okay, so we are using the same sorting array to deal with diverse algorithms, which is a very important spirit of building specialized accelerators. You want to have some basic primitive, like the sorting array, okay, in the red, to deal with many different algorithms within the same domain for this domain-specific accelerator. Okay. And similarly, if you are calculating the kernel map for W11, okay, so here we need to move it in the -1 dimension. Okay, and then we do the merge sort to find the intersection for those common non-zeros. Okay, and finally, we can find P0 and P1 and Q0, P4 and Q3 are corresponding to this W11. Okay, so using the same sorting array, we can deal with diverse algorithms and achieve pretty exciting speed up compared with the 2080 Ti, the Zion CPU, and plus TPU altogether. Okay, to summarize, we have discussed this full stack optimization from algorithm side using point voxel CNN and 3D neural architecture search to the software, right? Using the torch sparse to which is a new GPU kernel to accelerate the inference of point cloud, followed by the hardware accelerator, the point ACC, that can use the same sorting array to deal with diverse algorithms in point cloud. So in next lecture, we are going to introduce efficient video understanding and also these GAN models, okay, to continue with our journey to reduce the redundancies in neural networks and for these application-specific optimizations for efficient AI computing. Okay, that's all for today's lecture. Feel free to join our office hour, and today is the deadline for homework 3. Hope you all enjoyed it. Thank you.